Hello everyone and welcome back to another video of the Hidden Quantum Champions. Light, especially controlled light like laser light, is at the very heart of a lot of the new technology that is part of this second wave of quantum technology in sensing, in communication and in quantum computing. Why is that? You, for example, need light to create these NV center based sensors, to measure those NV center based sensors. You need light to actually create entangled photons, which you want to use for this quantum key distribution and for the quantum communication, which is mainly based on light. And you also need light in order to control cold atoms like Rydberg atoms or ions in your quantum computers. So light plays an important role, and looking at the supply chain, actually the light producing companies, so companies that are making lasers, that are making frequency comps, they're at the very heart of this second quantum revolution. Today's company is not an exception of those. Today's company is exactly sitting there. So they are one of the drivers, one of the beating hearts of this second quantum revolution, because they are producing products that the companies rely on, that are building these sensors, communication devices, and also some of the computers. Today we are looking at Vescent, one of the companies that is working on those optical solutions. And if you want to learn more about that, if you want to understand how a frequency comp actually works and how all of that plays together, then you are exactly right for today's video. So let's dive right into Vescent. And here we are on their website. So here also it says, you see in the background some video running with, I think, the components being conditioned in some conditioning chambers, some measurement labs here where they're testing stuff. We will go into the details of that in a bit. Here you see the main products, so frequency comps, lasers, and then controllers driving quantum 2.0 solutions. So quantum 2.0 refers to the second quantum revolution. The first quantum revolution brought us lasers like the ones that we know from our pocket lasers, but also the ones that we have in our CD players and so on and so forth. So basically the first quantum revolution was bringing quantum effects into technical devices. And usually these are collective effects. So lasers, they are collective excitations of electromagnetic waves. Electromagnetic waves are light, and the laser basically uses a collective excitation to create light at one specific wavelength. For example, a red laser creates only one wavelength in the red spectrum. So if you split it in the spectrum, if you're looking at sunlight, you see a rainbow. If you're looking at a laser, you only see one single line. Now, this is for the first quantum revolution. In the second quantum revolution, we are talking about manipulating single atom states, so single quantum states, so not anymore collective, more or less. And that can be, for example, to create entangled photons, so just a pair of exactly two photons. That can be quantum computers where you are trying to flip a single qubit, a single quantum bit from one state to another in a very controlled fashion. Or in an NV center, for example, as an example for a sensor, you're looking at a single NV center, so more or less like a molecule embedded into a crystal that you can manipulate with light, and that has some influence or is influenced by magnetic fields. So in all of these cases, lasers and frequency comps plays an important role, and that's why these products here, they are very much needed to build these laboratories. So here you can also see they are being used both in scientific labs, but also already in the field. Quickly about the solutions. So they have laser stabilization, so peak lock and side lock, pound Trevor Hall and offset locking, optical clocks, so low phase noise radar, precision timing, and then back up to GPS, short term and long term. And then cold atom science, so magnetio-optical traps, Bose-Einstein condensation, atom interferometry. Let's quickly take a little step back and talk about what these frequency comps are, how they are actually being used, and all of the things that are going around it. So first of all, let's quickly talk about lasers. a laser, as I said before, is a source that creates only a single wavelength of light. So how does that usually work? You have, for example, a specific transition. Let's say we have a little diode, a diode laser, a continuous wave laser, so the one that you have usually in your laser pointer. You are inside that creating a transition that can create a transition between different electric levels that can create light. So let's say you have a silicon crystal, you put some donor in there, and now the donor actually creates another electronic level. You can excite an electron up into that level, and then when it falls down, so in that case you're talking about a combination, a recombination of a hole and an electron, then you can actually, let's say, take an electron down in energy again, and this reduction in energy has to be compensated somehow because there's energy what is it called? Energy conservation. Energy is conserved, and that means you have to produce, or you have to remove this energy in some way, and that's usually then happening by creation of light, so of a photon. Now this mechanism itself is an LED. That's what you know from your smartphone, for example. When you have the little camera on the back, there's an LED on there which is used as a flashlight. You have LEDs everywhere, right? So that itself is not a laser yet, it's just a light source. And it's a monochromatic light source, so a light source that produces mainly one single frequency in the light spectrum, one single color. Now you can add a so-called cavity around that. What is a cavity? A cavity is basically a place where you can bounce these created light waves back and forth. So you take two mirrors like this that are parallel to each other, and now if you have a photon, it can bounce back and forth between those two mirrors, a little bit like in the old Atari game where you have the ball and then you're moving the pedals back and forth to kind of have it bounce back and forth. Just the light is like bouncing back and forth between these mirrors until it at some point gets absorbed. Now, if in between those mirrors you're having your active material, the one that produces the light, like for example the LED, you can now create a state where basically everything gets synchronized. So basically now one photon is emitted and it starts bouncing back and forth, and then a second one is emitted, and there's a certain mechanism that locks those two together in terms of their electromagnetic properties. So basically they are synchronized with each other, you could more or less say. Now that itself is a closed system, right? So you wouldn't see anything from the outside. But if you, for example, make one of these two mirrors here a little bit transparent so that it leaks out a little bit of the light, then you will actually see that there's like highly coherent laser light coming out there. So what do I mean by that? It means that not only the photons have exactly the same wavelength, but they're also like swinging in the same phase. So they are all like having the same wave pattern. They all go up and down. Well, in the electromagnetic field, they're actually not going up and down, but they're polarized and they're all working in the same way. So that's for a standard laser. However, these standard lasers, there are certain things that make them, let's say, difficult to work with. Let's think again about our little diode laser that I was talking about before. Now, when you start it, there's not much light in there, right? And the laser itself is at normal room temperature, ambient temperature. Now, when you turn it on, things start to heat up, right? And the heat actually causes some change in the size of your cavity, because at some point there's like small expansions due to heat, similar to when you think about, like water. Water has this anomaly, right? That when you freeze it, it actually expands a little bit in size. And that's why you shouldn't ever leave water inside glass bottles, for example, in your car when it's getting cold outside, because when it starts to freeze, it expands and it will just explode the water bottle. So the same thing is happening with all materials. When you heat them up, usually they expand. That's a little bit different between water and others. When you heat up a piece of metal, for example, it will just get a bit larger. And the same is happening for this laser cavity now. So it gets a little bit larger when it heats up. Maybe also the room temperature is changing. So you have these slight fluctuations, these changes in the size of your cavity all the time. And that can create some issue, because now what is happening is you're basically changing the properties of your laser light. So you need to be able to somehow detect this, that this is happening, and then you need to compensate for it. The compensation part is easy. You can use so-called piezoelectric motors, so like little crystals that can change their size based upon the electricity that is applied to them. Or vice versa, if you are changing their size, you create electricity. That's, for example, used in the gas lighters that you have usually. There's like this little button that you press, and then there's a little spark created in the lighter. That's basically a piezoelectric crystal that you trigger by basically pushing the button, and that creates a little high voltage peak that creates then a spark, which then lights up your lighter. And vice versa, if you would apply electricity to those crystals, you can change their size very minimally. And that's actually what allows you to tune those cavities to a very, very precise amount of distance change. Now, if you are looking at this so now you have the mechanism to change the size of your cavity, but how do you actually know that this change is happening? And that's where the frequency camp comes in. The frequency camp is one of the later inventions in the whole optics domain. It has been rewarded with a Nobel Prize also. And I think one of the founders here was actually in this exact lab where the Nobel Prize was rewarded to or granted to. But we will come to that part later. The frequency camp basically produces light pulses. So it is a usually a so-called picosecond laser. In my times when I was working in research, I had once the experience to work with a femtosecond laser. A picosecond laser is even more interesting. So what does that mean? Well, seconds we all know is a time measurement. Milliseconds is 10 to the minus 3, so that's even shorter. Then there's microseconds, 10 to the minus 6. Nanoseconds, 10 to the minus 9. Then you come to the femtoseconds. This is 10 to the minus 12, 3 orders of magnitude lower again. And then if you go to the picoseconds, it's minus 15, so even shorter. So these are very, very short amounts of time. And now what the picosecond laser is doing, it basically shoots pulses at these very, very short amounts of time. I can also explain to you in another video maybe. If you're interested in that, let me know down in the comments below how such a picosecond laser actually works in detail. You can of course also read it up or ask your AI that you trust. But it creates these very short pulses, usually in the span of something like 10 to the minus 6, 10 to the minus 9. So let's say 10 nanoseconds. Every 10 nanoseconds you get such a pulse. The interesting thing about those pulses is they are actually, even though they are created by a laser, they are very broad in terms of their frequency spectrum, in terms of their wavelength. How can that be, right? I said before that the laser only produces one specific wavelength, and now I'm telling you if you have a picosecond laser, it creates a lot of different wavelengths. Well, that has to do actually with the fact that there is some mathematical property of the universe which we call the Fourier, there's an algorithm that describes mathematical property of the universe called the Fourier transformation. What is that? The Fourier transformation is basically translating between, for example, the time domain and the frequency domain. So what do I mean by that? Let's take one step back. Let's think about music. When you are, for example, listening to your favorite song on Spotify, Apple Music, whatever, you're basically living in the time domain. So you're hearing different frequencies that are produced by instruments, by singers that are creating sound waves, right? Sound waves are a different type of wave, but they're also waves. And these ones you are consuming over the time, right? So also when you listen to me now, while I'm speaking, I create different frequencies with some vibrations here, right? And then these frequencies, they are recorded by a microphone in the time domain, but actually, in order to get them more efficiently delivered to you, what is happening is this time domain is being transformed into a frequency domain. This is, for example, the idea behind the MP3 compression algorithm. So you are basically moving from the time domain into the frequency domain. Then you can remove certain things from the spectrum, so you can save a lot of storage, or you can optimize your bandwidth. And then on your end device, it gets translated back from the frequency domain into the time domain so that you can actually listen again to what I was saying. And some of the information is going to be removed, but it's not like any relevant information is removed, so you can still figure out what I'm trying to tell you. Now this is for sound. This is also possible for image data. So there are also image compression algorithms that use the Fourier transformation to compress or to remove data from images so that you can move them back and forth more efficiently. Now the same thing can be applied to light. So if you are looking at the light frequency, at the laser, a laser usually produces one exact frequency, but then if you're looking at the shape of these pulses, right? So you have these very narrow rectangular pulses, more or less. So you have some light that is coming out at a very short pulse, like a photo flash, right? But very, very short. And now what it means is, from a Fourier transformation point of view, if you're transforming back this very short pulse, which is just one short peak of laser light, into the frequency domain again, then you will see that actually you need a lot of different light frequencies to create such a short pulse. And that's exactly what is happening in this frequency camp. So you are creating those very short signals, but then in turn, these very short signals, they're composed out of a lot of different light frequencies. So they're basically a broad spectrum. And now what can you do with that? Well, you can actually have it interfere, for example, with the laser light that I was talking about before. So now you can take this frequency camp or a picosecond laser, and you can take the continuous laser that I was talking about before. Now you merge both of the laser signals. And what is happening is interference. So both of these signals, they will start to interfere with each other. And now, because of the fact that one of them is basically a continuous light and the other one has this frequency camp property, so every 10 nanoseconds, for example, you have one of these pulses which are coming in, now you get a beating pattern. So now both of these waves, they will interfere with each other and they will create another wave that has a specific frequency. And usually this frequency is much, much lower than the frequencies that I was talking about before. So it's not in the picosecond range or in the femtosecond range. I mean, if you translate back and forth between frequency and time, right? But it's usually in the megahertz range. So megahertz is much easier to actually work with in the electronic domain. So with that, you can now basically figure out how the phase of your continuous laser is changing, because it might change from something like 20 megahertz to 21 megahertz or to 19 megahertz. And then you can trigger a compensation within your continuous laser, within your cavity, to kind of counteract on that. Now, this is extremely important because now you have a way to synchronize across all of the different lasers in your setup. And usually you have a lot of different lasers that you want to be synchronized with. For example, if you're looking at these cold atom science experiments here, right? What you want to do is you want to cool down the atoms. You want to trap them in a certain space. So now you need all these different lasers. You have different cooling mechanisms, right? I think I talked about it before in another video. If you haven't seen it, check out the Hidden Quantum Champions playlist. But you have the sideband cooling, but also different other cooling mechanisms. And for these things, you need a lot of different lasers. And now with a frequency comp, you can actually compare all of those to a single reference to the frequency comp. And that allows you to synchronize and to operate on these very precise levels, which you need to actually create these very low temperatures of like 50 nanokelvin, for example, here. Because for that, you really need to make sure that you're only sending a very specific frequency of light, for example, in this Doppler sideband cooling, to actually cool down the atoms. Otherwise, you start heating them up again. So that basically requires this frequency or this overall stabilization. And that is something which you need the frequency comp for. About optical clocks are more or less the next step of these well understood atomic clocks. I've talked about them in the previous video, so if you haven't seen that one, go ahead and check it out. And these optical clocks here, they also need a lot of stabilization, and that's again where the frequency comps come in. So which markets is this relevant for? If we are talking about clocks, we are talking about timing, right? Quantum timing that relates to also GPS. And that's because basically the GPS is heavily relying on a precise timing on these atomic clocks. Quantum computing, I explained to you before. Precision metrology is related to the quantum sensing, right? There's the precision sensing as well. The quantum networking I mentioned previously as well heavily relies on optical technology. And then you have the collaborative research mentioned here as well. A couple of cases of their impact, so quantum navigation, defense, and novel applications as well. And then down here we have the news section. I'm recording this beginning of June 2026. And you see, well, the latest news is from May, so very much up to date. Innovation Award about the rubric comp, and then also upcoming events, 1st of June, APS DAMOP. Furthermore, we only find the typical things down here. So there's a newsletter available and all of the relevant resources like application notes, manuals, research papers. You find things about the solutions, products, company, and so on down here. Let's quickly go into the solution space. I think I've talked about that before, right? So maybe we don't need to go exactly in there. Let's quickly check out the product. So frequency comp, I think I've mentioned before. They have two different ones here. So there's the Ruby comp and the Ruby color. Here, I guess it explains a little bit how the frequency comp works. So here you see those very short pulses, right, in the femtosecond pulse regime. And those themselves, because they have this sharp layout in the time space, because they have this very short time frame here, you need to actually compose them out of a lot of different frequencies to create this very sharp pulse here. And that's what, in hindsight, creates this broad frequency here in terms of light, right, in terms of different colors. And that's what I was trying to explain before in a much nicer graphic here. Here you see, I think, the correlation between these two, the repetition frequency and the offset frequency. These are then being used for this beating mechanism. I'm not sure if this is explained somewhere in here as well. I will not go through all of the details now. And then you see here the marine navigation as an example, Harrison clocks, and how those different clocks have been used over the course of time and why this is important. And then, there's again something here on the spectra, the Fourier transformation explained in even further detail. Actually, it's a very nice thing to see that all of these physics concepts are also explained here. So I think this is a very valuable resource if you want to learn a little bit more about the underlying mathematics and why that plays a role. And then here, I think we have here it says continuous wave and pulsed lasers. So maybe we come to this point where they are brought to interference now. Yeah, and I think here you see all the the different applications, right? A stabilized self-referenced optical frequency camp enables incredible applications. These are graphically shown in the figure below, which is adapted from a paper by Scott Diddams et al. And then here we see the different applications. So yeah, there's even more stuff that this is useful for. And I think over the course of time, whenever you need lasers in something, I think the frequency camp is a very important piece of your toolbox. And then again, we see down here the different applications and the different products that they have. Let's quickly go into the quantum application so that we've seen that once, because we are at the Hidden Quantum Champions here, right? So we gotta also check out the quantum part of it. So enabling and scaling quantum 2.0 for national security, securing supply chain for critical technologies, resilience in GPS compromised environments, next generation radar and sensing technologies, national economy, rebuilding US manufacturing infrastructure, providing and creating high-skilled jobs, enabling economic global leadership. Global leadership, the NQI accelerated US quantum advancements, NQI authorization required, authorized chips, ACT quantum tech hubs, elevate quantum Rocky Mountain West. And then, okay, what do we have here? Again, optical clocks for backup to GPS, because you need precision timing for certain things, for example, for the GPS, right? Then quantum oscillator empowered radar, so for slow and small adversary drones, balloons, etc. Then tactical signal intelligence sensing, enabling and improving quantum computing, and then complex continuous environmental sensing. They all need this kind of technology. Okay, so that's about the quantum part. We also see the optical clocks. They are similar again to the atomic clocks that I was talking about in the previous video. If you haven't checked that one out, go ahead and do so. And the cold atom science, I think I've also talked about in a previous video. So go and check out the previous videos as well. Resources, we don't go through all of these ones now, but let's, as per usual, also quickly learn something about the company itself. And for that, let's go into the story of the company. So our story, and it starts with this very nice photo here of a little, maybe a little office, maybe a little apartment. Let's learn about that. So our story. This little brick building in downtown Denver, Colorado, was a garage. It is so old that it used to be the track room for horses, and it is also the very first lab of Vescent Technologies, the coolest laser lab on the block. From Vescent's humble beginnings, our founders, Scott Davis, Scott Romble, and Mike Anderson, have transformed Vescent into a key player in the quantum supply chain. Driven by a passion for innovation, a vision for the future of technology, and an aggressiveness that pushes the envelope of quantum performance to help customers solve key needs, these three physicists created something bigger than a lab. While Davis and Rommel continued to lead, their journey remains in an inspiration as Vescent brings groundbreaking laser systems to the world. Vescent Technologies Inc., a privately held company, was founded in 2002 to develop and manufacture technologies in waveguides, electro-optics, tunable lasers, and electronics for precision laser control. In 2016, Vescent successfully spun off its waveguide and beam steering technologies. We are located in Golden CO, Colorado. Our closest proximity of GILA, NIST, the University of Colorado, and several other government laboratories facilitates collaborative development. Our R&D and manufacturing facilities house a 1,000 square foot clean room for lasers and electro-optic assembly, multiple optical laboratories, electronic development facilities, and a machine shop. We also are corporate members in a number of professional societies. Scott Davis leads Vescent as a president and CEO after receiving the reins from Mike Anderson. Mike honed his expertise in his field as a postdoctoral fellow in the research group of Nobel laureate Eric Cornell and Carl Wieman of the University of Colorado Physics Department. He was primary author of the publication that first reported on the creation of a Bose-Einstein condensate. So you see there's a lot of history within the company and a lot of, let's say, spirit of innovation. Quick look at the management team, and again, this company, as you could see also from the previous page, right, there is a history already behind that. It's not spun off 2 years ago, but like in 2002, so there's quite a bit of time that they've been on the market. It's not something that is IPO'd. It's a privately held company. And here you also see there's a lot of expansion, right? It went from this very little tiny garage to now 1,000 square foot clean room space with all of this fancy equipment. And as such, it is not a surprise that we see that there's also a whole, let's say, set of leadership team available here, right? You not only have a CEO and a CTO, but also COO as you're shipping products. Everything has to also be let's say, brought to the market. So you have a VP of sales and so on and so forth. So it's a proper company with all the proper company functions. And you also see the people here, they seem to have, that's not necessarily their first job, right? So they have also some experience in the market. The company is very well established. Good. I think that's everything that I wanted to show you about Vescent as of today. So again, they are, let's say, at the very backbone of a lot of this new technology, second quantum revolution, technology revolution, because they are building basically the optical equipment that goes into all of these different things, right? And that's where their technology is playing a very basic role. And that's also why I think they play, let's say, an important role, even though they are probably a bit hidden, because you usually don't see their label on the machines on, like, I don't know, a big ion-based quantum computer or anything like this, right? But very likely there are some components of theirs inside these machines. I hope you liked today's video. If so, please make sure to give it a thumbs up. If you stayed all the way to the end, there is a high likelihood that you might also like the next one. So make sure to subscribe to the channel. I'm, as always, looking forward to see you again in the next one to discover some more cool quantum physics. As per usual, stay hydrated, and I'm looking forward to see you in the next one. Until then, bye-bye.